Hello everyone, welcome to the lecture on transistors. Today we're going to cover the two kinds of transistors, the NPN and PNP transistor, and we're also going to analyze their behavior and take a look at the half-wave rectifier as an example of where we use semiconductors in general. Now first of all, there's two kinds of transistors, BJT and FET. We're going to cover BJTs, or bipolar junction transistor, pretty exclusively in this course. The FET, or field effect transistor, they're important too, but we're not going to cover them in this course in a lot of detail. Just know that the field effect transistor uses applied voltage rather than applied current like BJTs do, as a rule. All right, so the construction of a transistor is 3 layers of semiconducting material alternating between p-doped and n-doped layers. The order of the layering determines the effects of the component. Because there are 3 layers and 2 types of construction material, there are 2 types of BJTs. There are NPN, which has layer order NPN, and PNP transistors have order layer PNP. Shocking. The schematic symbols for each type are shown to the right, where the PNP symbol has a layer pointing toward the center of the symbol, and the NPN has the arrow pointing away from the center. So there is one huge difference between a transistor and every other component we've used so far. The transistor is a 3-lead component. We require 3 connections with the rest of the circuit in order for the transistor to work. So before we go on, a note about the order of the leads. Transistors are manufactured as a semi-cylinder with the 3 leads in a row, and it's very important to know exactly which lead is which. And each transistor model is not guaranteed to have the same ordering as any other model. The wiring I've included here is for the 2N2222 NPN transistor, which is different from the P2N222 model. So this can get a little confusing, but every time you get a transistor or you need to use a transistor, it's very important to read the spec sheet and look at the wiring diagram so you don't order it incorrectly. All right, now on to some physics. The NPN transistor has a thin p-doped layer sandwiched between 2 n-doped layers. Just like a diode, we have a depletion zone at each of the interface regions, and new potential energy after the electrons do their thing prevents flow across those 2 boundaries. So the 2 N materials are of the same kind, so if we just apply an external electric field across the extreme sides, we won't get a flow of current because they're not overcoming, the electrons won't be able to overcome that potential energy bump in the center of it. So what we would need to do instead is include a current into the central p-doped region to include electrons in there to lower that potential energy, and then we can allow the current to flow across the 2 outside edges. So you need 3 terminals, 2 for the electrons to flow from one side to the other, and then the third one in the center controls the ability to allow that current to flow. And then PNP works basically the same, except for instead of adding current to the central layer, we're going to need to remove current from the central layer. So let's take a second and think about what this third terminal really means in terms of construction. In a NPN, if we apply current, our transistor suddenly is on. If there's no current, it's off. It can't flow. There's no current flowing through it. It's off. For the PNP, if we are allowing current to leave that central region, we're allowing current to flow in general, so it's on or off, which is 2 states of operation, which seems an awful lot like binary. So the ability to control the current in this manner is the foundation of all modern computers and all systems that rely on binary systems, on binary components, you know, like every single piece of electronics that exists right now, except for quantum computers, but that's for another class. So let's look at some transistors just hooked up to some power supplies so we can get an idea of how we might analyze them and how they might work in the circuit. So for convenience, there is some commonality between the naming of the terminals. Whether or not it works out to this order in real life or not is up for grabs depending on the component. But at least as far as the circuit diagram is concerned, there are 3 terminals. The one with the arrow is always called the emitter current, every time. The central one is called the base, and the remaining lead is called the collector. So whether or not it's voltage or current, it would be called collector voltage, collector current, base voltage, etc., etc. So we can see just right off the bat, based on these wiring diagrams, that on the NPN transistor, the collector and base current both flow to the component, and then the emitter current flows away. And then the PNP diagram shows the opposite. The collector and base currents leaves the component and the emitter current arrives. If we are looking very closely, we might be able to tell that we only have one complete current loop, even though we have 2 voltage sources. Well, the second voltage source acts mostly to absorb energy or provide energy to the central base and reduce the effect on the other. This, plus the energies required to overcome the band gap energy, remember our talk about semiconductors, result in some voltage and current relationships. So just based on those previous wiring diagrams and a little semiconductor physics, we can tell that the collector current is equal to the difference between the base and emitter currents. And this is important to keep in mind because it allows us also to kind of treat these as a gain. More on that in a moment. Another relationship is that the voltage difference between the base and the emitter, if we're using silicon, is 0.7 volts. And the difference between the collector and the emitter is 0.2 volts. And this is related to the materials used to construct the transistor. So if you don't have a germanium or silicon transistor, it's going to be something else. But as a rule, 0.7 is what you go to. It's the most common one. So as you can see here, there is the relationship. I'm just going to start over. Hello all, welcome to the lecture on transistors. We're going to cover 2 kinds of transistors, NPN and PNP, and we're going to analyze their behavior, and we're going to look at a half-wave rectifier as an example of where we can use semiconductors. So first of all, before we get into all of the transistor basics, I'm just going to say there are 2 kinds of transistors, BJT and FET, and we're going to cover BJT, or bipolar junction transistors, pretty exclusively in this course. The FET, or field effect transistor, we're not going to go over very much. They're important for lots of things, but in this course we're going to be mainly using BJTs for our circuits and calculations. All right, back to how they work. The construction of a transistor is 3 layers of semiconducting material alternating between p-doped and n-doped layers. And then the order of the layering determines the effects of the component. Because there are 3 layers and 2 types of construction material, there are 2 types of BJT transistors. These are NPN, which has layer order NPN, and PNP, which should shock nobody to learn has the ordering of P, N, and then P again. The schematic symbols are shown for each type on the right, where the PNP symbol has the layer pointing toward the center and the NPN, the arrow points away. Now there is one major difference between transistors and every other component we've used thus far. That is, the transistor is a 3-lead component. We require 3 connections with the rest of the circuit in order for the transistor to work. So before we go on, a note about that. Transistors are manufactured as a semi-cylinder with 3 leads in a row. It is very important to know exactly which lead is which. Each transistor model is not guaranteed to have the same ordering, even within manufacturings or similar lines. I've included the wiring diagram for the 2N2222 NPN transistor, which is different than the wiring guide for the P2N222 model. So these are both manufactured by the same company, and they both do very similar things, but the wiring diagram is different. So when working with transistors, it's very important to read the spec sheet. All right, now on to some physics. The NPN transistor has a thin p-doped layer sandwiched between two n-doped layers. And just like a diode, a depletion zone occurs at the interface regions, and the new potential energies prevent the flow of electrons across the boundaries. The two ends are of the same type, so if we just naively apply an external electric field, it won't help here. We instead need to also apply a current to the central p-doped region to flatten that potential curve. This allows an external current to control the flow of current across the two main terminals of the transistor. And then the PNP transistor is basically the same, except for the middle layer is an n-doped and the outer layers are p-doped. And the same thing happens in terms of the depletion region, but now instead of applying current to the middle, we need to remove current. The middle layer has an excess of electrons that need to be removed before we can keep funneling electrons across the entire component. So let's take a second and think about what this third terminal means. If we're not supplying or removing current from that third terminal from the central region, our transistor is effectively off, right? There's no current being allowed to flow between any of the other parts. But if we suddenly allow current to flow to or from that central region, we can allow current to flow across the other components, the other parts of the component as well. So that's two states. Well, that's binary. So transistors and the ability to control them using current and external effects gives rise to all computer technology that we use today, except quantum. But transistors are foundational to everything in cell phones, desktops, laptops, all that stuff. All right, now let's analyze them a little bit so we can figure out how to use them inside of circuits. First, we're going to look just at transistors hooked up to some power supplies. For convenience, no matter the type of transistor, the lead with the arrow on it is always called the emitter. And the central lead is the base, and the remaining lead is the collector. And this naming convention applies to voltages and current as well. So if you wanted to know the voltage going into the transistor across the collector, you would just call it the collector voltage, and so on. So we can see from the NPN diagram that the collector and base current flow toward the transistor, and the emitter current flows away, and this makes sense. Emitter emits, it leaves. And then collector, we need to collect it so it comes in, and base is there to allow it to happen. But for the PNP transistor, it's the opposite. The collector and base flow away, and the emitter comes in to the transistor. So just keep that in mind when doing wiring diagrams for these types of circuits. And now for current loops. With these wiring diagrams, with these circuits, we might be able to tell that there's only one complete current loop made, even though we have two voltage sources. Well, the second voltage device acts only to absorb energy and reduce the effect of the other. This, plus the energies required to overcome the band gaps or potential energies, result in some voltage and current relationships that we're going to go over now. So just based purely on the previous wiring diagrams, we can tell that the collector current has to be equal to the difference between the base and emitter currents. We can also base this on Kirchhoff's current law applied to those previous circuits we were just looking at. And then the voltage difference between the base and the emitter, if we were using silicon, is 0.7 volts. And the difference between the collector and emitter is 0.2 volts. And this voltage difference is related to the materials used to construct the transistor, so their physical properties. Of course, this applies to silicon transistors. If we're using a different material, we need to use different voltage differences. That's another reason why it's important to read the spec sheet for all transistors. And also, another thing we need to worry about is current gain. Due to the properties of semiconductors, more current comes out than what we started with. And for the most part, gain is a direct linear relationship between the collector and base current. This is important since if our components are very delicate, then this is bad. We need to find a way to reduce the current because we don't want to start shoving in more current than what our stuff can handle. But if we need more current to power something, this is good. Many times when we're attaching a motor to something, the motor is going to require a certain minimum current to work, and using transistors effectively is key because of this gain. Now, it's important to state that transistors are still used widely to power things that are delicate. It just requires a little bit of extra thought about what else we attach to the circuit so we can minimize that, that applied current. Maybe we're going to be using a voltage divider as we discussed previously in this class. All right, so if we remember from the lecture on diodes, current is also proportional to applied voltage. So in order to ensure consistent behavior in current and make sure that we're operating in a region where that gain makes sense and is constant, we're going to need to operate in a region called saturation, where saturation is achieved by applying enough voltage so that our output current is at a maximum. So we're going to try to apply enough current and enough voltage to our transistor so that it's at its maximum output, so that we don't have random fluctuations caused throughout. And if that doesn't make sense to you, go back to the diode lecture and think about Shockley and the Shockley diode law. All right, so let's run through how to find the appropriate voltages and currents to apply to a transistor to make sure that we are operating in saturation. First, we're going to find out how much our collector current is since we have all the parts for that here in our diagram. We know that we're feeding 10 volts into it across a 1 kilo ohm resistor, 10 volts to 1 kilo ohm, and we have 0 on the emitter, so effectively at the transistor we have 0 volts there as well. So first step, find that current. The voltage is 10, and the difference between the collector and emitter is 0.2, remember from our semiconductor properties. So that drop between collector and emitter 0.2 needs to be taken into account here, which gives us 9.8 volts across a 1 kilo ohm resistor. It gives us 9.8 milliamps. And now that we know our collector current, we can use the gain relationship to determine the needed base current. If our gain is 100, we divide the collector current by 100 to find 0.098 milliamps. So now we know how much we need for the base to work properly. The current input to the base is the voltage over the resistance on that branch. But we're looking for that voltage, and we also need to take into account the 0.7 volt loss from the semiconductor properties, giving us our equation of base current equals Vn minus 0.7 over 10K. Now we just need to solve for the voltage. We do so, we find out it is 1.68 volts applied to our base to give us our saturation voltage. Now in practice, we would want to apply more than this, 2 or 3 times more, maybe 5 if we're not being super delicate about it, because we don't want any fluctuations in that input voltage to put us below the saturation region. Because if you remember from the Shockley diode equation, it's an exponential. So even a small dip in that current, getting us out of saturation, is going to result in a pretty tremendous drop in the current, which might just wreck our circuit, or at least its intended purposes. So now we're going to go over a half-wave rectifier, which is a very common circuit that makes extensive use of diodes. And what this circuit does is it stops any negative current from flowing through to that LED on the side. It doesn't have to be an LED, it can be any other kind of component. LED is just for illustration. So we have an AC generator, and when it is emitting positive current from the plus side, The diode is forward biased and allows current to flow through. And the current then activates the transistor, which then allows the current from the DC generator to turn on the LED. When the AC generator is emitting negative current from the plus side, or it's positive from the minus terminal, the diode is reverse biased and no current's going to flow, because remember, the diode only wants to go in a single direction. The LED will not turn on then. So I've included a plot underneath this circuit diagram where the AC generator output is the solid green line, and we can see it fluctuating from positive to negative pretty consistently. And then the solid blue line is positive when the AC wave is positive, emitting out the plus side, and 0 when the AC wave is negative emission out of the plus side. And that is taken across the LED. So the diode effectively stopped it from negative voltage going across the LED, which might damage most LEDs. They're pretty delicate in terms of reverse biasing. From this, we should also be able to tell that the LED is going to blink at a rate of 1/2 the frequency of the AC generator. I encourage you to build this circuit in multisim, play around with it, see if you can get it to do other things. Maybe include a capacitor in series with a resistor to try to slow it down and get it to smooth out a little bit. You might also try to make a full wave rectifier, which might show up on a test someday. So these are useful. These half wave and full wave rectifiers are very useful for timing circuits, especially if you're timing some kind of input. There's lots of other uses for them, especially making sure that we don't have to deal with negative current inside of delicate electronics, which might not be able to handle them so well. Well, I hope that was a good introduction to transistors, but that's all for now. Bye.